Welcome students. Today we'll start our discussion with carrier concentration in intrinsic semiconductor. There are two types of carriers exist in case of an intrinsic semiconductor, that is electrons and holes. Today we'll concentrate on deriving the expression for electron concentration. In the next class we'll continue the discussion with hole concentration. As there are two types of carriers exist in an intrinsic semiconductor, we need to calculate two types of carrier concentration. The first one is electron concentration and the second one is hole concentration. Before going into the derivation, let me ask you one question. How the carriers occurs in case of an intrinsic semiconductor? Yes, it is due to electron-hole pair generation. As we have already discussed, in case of intrinsic semiconductor, the carriers are created due to the generation of electron-hole pairs. In this process of electron-hole pair generation, what happens? Some of the bonds breaks in the semiconductor and the electrons becomes free and move into the conduction band, leaving behind an empty space in the valence band, which is known as holes. From this we come to know that the free electrons are present in the conduction band. So what is the electron concentration? This is nothing but the number of free electrons per unit volume of the conduction band of given intrinsic semiconductor. That means we have to calculate what are the number of free electrons present in the conduction band per unit volume, and that is our electron concentration. Generally it is represented by a letter N. Here this is the valence band and this is the conduction band. For this calculation, we will be considering two energy states in the conduction band. The first one is at energy E. So this is the energy state with energy E. Next, we will be considering an energy state with energy E plus dE. And the number of free electrons in between these two energy states is given by dN. So dN is the number of free electrons per unit volume having energies between E and E plus dE, and as we are calculating the electron concentration, this is in the conduction band. So whatever the electrons present in between these two energy states, that is E and E plus dE, that is represented by a letter dN. This is a small interval of energy. That's what we are taking the carrier number as dN. How can one obtain this small number of carriers present between this E and E plus dE? For this calculation, we need to calculate two things. First, we will calculate the number of states available between these two energy states, that is E and E plus dE. The second quantity we need in this calculation is the probability that the states are occupied by an electron. Z of EdE, this is the density of energy states between E and E plus dE. This quantity gives us the number of energy states available between E and E plus dE. Once the number of states are known, then we have to see what is the probability that each of those states are occupied with electrons. That is given by F of E, which is the probability of occupation of electrons, and this probability function is given by Fermi-Dirac function. After knowing these two functions, that is density of states and probability of occupation of electrons, we need to multiply these two functions to obtain the number of free electrons per unit volume. So dN is equals to Z of E, this is the density of states, and F of E is the probability of occupation of electrons. By multiplying these two functions, we will be getting the number of free electrons. And these free electrons are the electrons present between these two energy states, that is E and E plus dE. Further, the density of states is given by this function. The derivation of this function is given in your solid state physics. If you want a derivation here also, then put your queries in the chat box so that I will come up with a video for the derivation of this function. So this is the density of states, which is given by 4 pi by h cube 2m to the power 3 by 2 e to the power half dE. This gives us the density of states around the energy state E. Here h is the Planck's constant, m is the mass of the carrier. At this point, we will be doing some modifications because the energy we are interested for is starting from the bottom of the conduction band, because we are calculating the electron concentration, and as I have already told you, the free electrons in case of an intrinsic semiconductor exists in the conduction band, and holes, those are found in the valence band. And the conduction band starts with an energy EC, which is known as the bottom of the conduction band. Below EC there are no free electrons available, and hence we will be calculating the electron concentration above EC. So our energy starts from this value EC, which is nothing but the bottom of the conduction band. Because of this reason, we will be shifting our reference point from 0 to EC. This leads to a modification over here. Here I have written E as E minus EC. Let us understand this concept with a simple example. Let this is the reference at 0. If it is 0, this is 1, 2, 3, 4, 5, like that. While I am taking 0 as the reference, these values are 1, 2, 3, 4, 5. Now if I am shifting my reference to this point, that is 2, what will be the value of 3? That will be 1, because this is now our reference. So this will be 1, 2, 3, like that. 3 becomes 3 minus 2, that is 1. 4 becomes 4 minus 2, that is 2. 5 becomes 5 minus 2, that is 3. So all the values are reduced by an amount 2, because I have shifted the reference by 2. Similarly, in this case, we are shifting the reference from 0 to EC. So whatever the energy we are considering, that value should be reduced by an amount EC. And that's what I have done some modifications over here. This E I have taken as E minus EC, because we are considering the bottom of the conduction band, that is EC, as our reference point. This is the first quantity we need in our calculation, that is density of states. The second one is the probability. The probability of an electron occupying an energy state E is given by the Fermi-Dirac distribution function, that is f of E is equals to 1 by 1 plus exponential E minus EF by kT. Here we are calculating the probability of the electron occupying the energy state E. That's what this E over here. And this EF is the Fermi energy, K is Boltzmann constant, and T is absolute temperature. This is the probability function. We'll do some approximation over here. What is this K? This is our Boltzmann constant, which is given as 8.617 into 10 to the power minus 5 electron volt per Kelvin. So here you can see this 10 to the power minus 5 is a very small quantity. So if we will multiplying this T over here also for all possible temperature, this KT will be having a very small value because of this factor 10 to the power minus 5. If KT is much smaller, that means E minus EF is much greater than kt. We'll consider this approximation that E minus EF is much greater than kt. If E minus EF is much greater than kt, that means this numerator is much larger as compared to the denominator. If numerator is very high, then this exponential function will have a very large value as compared to 1, and hence 1 can be neglected as compared to this exponential function, because of which f of e, this can be approximated as f of e is equals to 1 upon exponential e minus ef by kt, because we have neglected this 1 with compared to this exponential function. Now if I take this exponential function to the numerator, I can write f of e is equals to exponential. This I am taking off, so it will be minus e minus ef by kt. Introducing this negative sign inside this bracket, I can write this function as exponential. This will become plus and this e will be minus. So it is ef minus e by kt. So the probability function f of e is equals to exponential ef minus e by kt under the approximation that e minus ef is much greater than kt. Now we have both the functions, that is the density of states and probability function. Using these two, we can write the electron concentration between E and E plus dE, that is dN is equals to Z of E dE. This is the density of states and this is our probability function. dN is the electrons lying between this E and E plus dE. But we are going to calculate the total electron concentration in an intrinsic semiconductor, which includes the states above EC. And this is the small function. In order to calculate the total electron concentration, we need to integrate this dN, and the limit starts from EC because we are interested for the states lying above EC. The lower limit is EC and we have to consider all the bands lying above EC. That is why the upper limit is top of the band. After integrating this function with this limit, we will be getting the electron concentration in case of an intrinsic semiconductor. Let us do this integration by substituting these values over here. We have obtained the density of states as 4 pi by hq 2 m star 3 by 2 e minus ec whole to the power half dE. Here this h is the Planck's constant. Me star is the effective mass of electron. E minus Ec, this we obtain by shifting the reference to the bottom of the conduction band, that is Ec. So this is the expression for density of states and the probability function is given by exp ef minus e by kt. Now we will substitute these two over here and do the integration. After substituting, what we will get? This Z of EDE is this one, this red portion, 4 pi by h cube 2m star 3 by 2 e minus ec to the power half dE. And what is f of e? F of e is this one, that is exponential ef minus e by kt. And here you can see the limit of the integration, the lower limit is EC and the upper limit, here it is the top of the band. I have changed that to infinity because if I am going up to infinity, that will definitely cover all the bands available above EC. Here in this integration, the terms encircled inside this circle is constants because 4 pi is constant, Planck's constant is again constant, Me star is the effective mass of electron, that is also constant. So this portion is constant and independent of the variable E. I can take this constant term outside the integration. So this constant term is taken outside. Inside the integration, we left with e minus ec to the power half exponential ef minus e by kt dE. Here this exponential term has two terms embedded inside. One is ef by kt and the second one is minus e by kt. We all know that e to the power a plus b is equals to e to the power a into e to the power b. So here it is exponential ef by kt minus e by kt that can be split into two terms. One is exponential ef by kt and the second one is exponential minus e by kt. Out of those two terms, the first one, that is exponential ef by kt, that is again a constant because the Fermi energy is constant, k is constant, temperature is independent of E. So this exponential ef by kt, which is a constant, that can again be taken outside the integration, and inside the integration we will left with exp minus e by kt. So this term was there earlier. From here this exponential ef by kt came out of the integration. Inside the integration we left with e minus ec to the power half exponential minus e by kt dE. Finally, we have to calculate this integration now. Here we will do some substitution to do the integration. What is that substitution? E minus EC is equals to X. This E minus EC, I took that as X. If I am taking this X, what will be E? E will be equals to, taking this EC to the right hand side, it is EC plus X. And what will be dE? dE is equals to dEc, that is a constant term EC, so that will be 0, and this is dx. So dE is equals to dx. Let us see how this integration will be modified after substituting all these values. These are the constant terms. Now inside this you can see this E minus EC, that is equals to X. So in place of E minus EC I have written X. What about this E? This E is equals to EC plus X. So in place of this minus sign, you can see it is over here. This E is equals to EC plus X. What is dE? dE is equals to dx. So these are the substitutions made over here to do the integration. Now we'll check how the limits are changing after changing the variables from E to X. When the variable was E, the lower limit was EC. Now the variable changed from E to X, we'll see what will be the lower limit. So when E is equals to EC, what will be X? EC minus EC, that is 0. So whenever that value of E was EC, that time X will take the value 0. So the lower limit over here is 0. Coming to the upper limit, this is infinity. So if I put infinity over here, infinity minus EC, that will be again infinity. So the upper limit is remaining as it is, that is infinity. So in this integration, we have done the modifications like E minus EC is equals to X, E is equals to EC plus X, D is replaced by dx. The lower limit changed from EC to 0 and the upper limit remained as it is, that is infinity. In this integration, let us again look into this exponential term. Here also we are having two terms. One is exponential minus EC by kt and the second one is exponential minus x by kt. Further, this exponential minus EC by kt is a constant quantity because EC is the bottom of the conduction band, which is constant, k is constant, t is also constant, and the variable over here is x. So exponential minus x by kt is variable, and the first term, that is exponential minus ec by kt, that is a constant term and hence can be taken outside the integration. So taking these outside the integration and merging that with this exponential term, this is exponential ef by kt and here it is exponential minus ec by kt. If we merge these two terms, this will become exponential ef minus ec by kt. And inside the integration, we left with exponential minus x by kt and x to the power half was there. So we have to do the integration. for this term now. This integration inside this red box that resembles with a standard integration, that is x to the power half e to the power minus ax dx. Integration limit is from 0 to infinity is equals to root pi by 2 a to the power 3 by 2. If you compare this to this x to the power half, here also x to the power half, this exponential minus x by kt, if you compare with this e to the power minus ax, what will be the value of a? A will be equals to 1 by kt, because here you can see x is there and a is 1 by kt. And to obtain the value of this integration, we need the term a to the power 3 by 2. So a to the power 3 by 2 is equals to 1 by kt to the power 3 by 2. Now substituting this value over here, we will get the value of n as n is equals to 4 pi by h cube 2 m star 3 by 2 exponential ef minus ec by kt. All these things are as it is. Only we need to substitute the value of this integration. And what is the value of this integration? That is root pi by 2 a to the power 3 by 2. So root pi by 2, that is pi to the power half by 2, and a to the power 3 by 2 is 1 by kt to the power 3 by 2. So here if I am writing 1 by kt to the power 3 by 2, that kt to the power 3 by 2 can be taken to the numerator. So this is kt to the power 3 by 2 pi to the power half by 2. This is the final expression for electron concentration after doing this integration. Now we'll do some further modifications into this. Let us see what simplification we can make over here. This 2 and this 4, if I'll cancel, I can write 2. And here if you can see this 2 m star to the power 3 by 2, kt to the power 3 by 2, this pi and pi to the power half, that can be written as pi to the power 3 by 2. And this hq, I can write it as h square to the power 3 by 2. So combining all the terms which are having the power as 3 by 2, I can write this as 2 pi m star kt to the power by h square whole to the power 3 by 2. Because this is pi to the power 3 by 2, so it is pi 2 m star kt to the power 3 by 2, so this is kt. HQ is nothing but h square to the power 3 by 2, so it is h square. So this whole term to the power 3 by 2, and what we left with? This exponential function, that is exponential ef minus ec by kt. So this is the simplified expression for n. Here we will do one more substitution. This term inside the circle is again a constant, because these two are constants. Pi is constant, m is star, that is the effective mass of electron, k Boltzmann constant is temperature, h is Planck's constant. So all these are constants, and hence I can take this as a constant nc, which is equals to this term. And this nc is known as effective density of states in conduction band. At 300 Kelvin for silicon, the value of Nc is equals to 2.8 into 10 to the power 25 per meter cube. Here Nc is the effective density of states. Density of states means the states available per unit volume. That's what this is, a number per unit volume, and the unit is per meter cube. So this is 2.8 into 10 to the power 25 states per meter cube. Now if we use this approximation over here, then n can be written as nc exponential ef minus ec by kt, where nc is the effective density of states in conduction band. So this small n is the number of electrons per unit volume, which is nothing but our electron concentration. This is the final expression for electron concentration in an intrinsic semiconductor. Here this Nc is equals to 2 into 2 pi m star kT by h square whole to the power 3 by 2, and EF is the Fermi energy, EC is the bottom of the conduction band, and K is Boltzmann constant, T is our temperature in absolute scale, and inside this NC, what is this m star? M star is the effective mass of electron that can be obtained from our energy wave vector diagram. And what else we left with, that is H is the Planck's constant. So if all these values are known to us, we can calculate the electron concentration at the given temperature. From this expression, you can see that the electron concentration changes with the temperature of the semiconductor because it is dependent on this T, which is temperature of the semiconductor. Let us conclude our lecture with a brief summary of what we have done. We have considered two states, one at energy E at another at E plus dE. Then we have calculated the density of states between these two energy and the probability of occupation of electron. Then we multiplied both the terms to get the number of carriers between these two energy states, and finally we integrated that from bottom of the conduction band to top of the bands, and we obtained this expression which gives us the electron concentration in an intrinsic semiconductor. Thank you all. If you found the video is useful, you can share the link with your friends so that they will also get the benefit. Also, don't forget to like and subscribe the channel and ask your friends also do the same. Thank you all once again.